Hi, welcome to the Signal Path. In this episode, we'll be taking a look at the Rohde Schwarz MXO-5 Series oscilloscope. It's their 8-channel, 2 GHz, 12-bit ADC system, built entirely end-to-end from their own ASIC, which means that their DSP is completely hardware accelerated, built on an 18-bit architecture, and this thing is ridiculously fast because it offloads all the complex FFTs and a lot of the trigger functions directly into a custom IC at 400 gigabit per second internally. It's a crazy bit of engineering. And because they control this end-to-end system, they have extremely low noise, very good linearity, and like I said, ridiculously fast with one of the shortest trigger dead zones in the industry. But I'm actually interested in looking at the entire architecture and looking at the acquisition board and see how they've put it together, what are the unique features, and then do some demos because it's a wonderful time to buy an oscilloscope. Oscilloscopes are no longer time domain instruments. All the big vendors now think in the frequency and time domain at the same time, allowing some really unusual triggering. In this case, you can do this really cool zone triggering both in the frequency and time domain that I want to show you. It's definitely a unique feature in this oscilloscope, and they're competing very well against each other. So let's take a look. And here is the Rohde Schwarz MXO-5 Series oscilloscope, 12-bit, 2 GHz, 8 channels, and you can see the individual channels, and they all have the light at the top of them which match the color palette that you choose, and all the buttons and everything are contextually colored as well, and they lit up depending on what is selected. And that's how you can have such a huge screen real estate, because the knobs and everything are used for all the channels at the same time. We have USB 3 ports, 3 of them in the front, and the logic analyzer inputs. Now, given the width of the instrument, there is no trigger in the front. The trigger, reference in, reference out, and the arbitrary function generators are all accessible here. Luckily, it's not all the way in the back of the instrument. It's actually right here on the side, so it's pretty easy to access. I really do like the new industrial design, the color scheme and everything, clearly well thought out. But let's take a look at the acquisition port. That's where a lot of interesting things are. Now we're going to take a look at some of the interesting design features more closely in a second, but as an overall architecture, there are a few observations. First of all, it's incredible that you can build a big board like this. This is 42 centimeters by over 28 centimeters or so, with so much mixed signal on a single PCB. There's a lot of functionality in here. And if you look closely, you can see some hardware replication. And that's because this is basically two MXO-4 series oscilloscopes glued together. And there's some hardware replication, which is immediately obvious. For example, this section over here and this section over here, they're essentially the same. And you could make two MXO-4 series with those sections alone. At the same time, you have the front end and everything fully custom designed, and everything is self-contained. So the acquisition, the triggering, the ADCs, and so on are basically their own subsystem. So putting them next to each other is somewhat easier. The only thing that's shared is this Xilinx Zinc FPGA with its own memory and so on, which is basically interacting with the entire system. There's a really cool analog front end, which we'll take a look at closely as well, and all the reference in, reference out, arbitrary function generators are also contained on this board. All the power management is also here. It's amazing that you can make all of this work. I'm not sure what the yield of a board like this is, but there is a lot going on it. And even the Ethernet and the USB interface are also all shared in here. I'll flip it to the other side so you can see the other side too, but we do have to take a close look at the architecture in a second. And here's the other side of the board. Some more of the USB ports are there. So even the user interface elements such as the USB are directly onto this board. And that makes it quite a bit of a mechanical challenge too, because you need to make sure everything wraps around correctly. Some of the additional traces to the data converters from the 8 front ends are also visible. The rest are just power management. And there's some cages around some critical areas, which we will talk about. So now let's go to the image and we can trace everything out. So here's a picture of our board, and we can take a closer look at it. Now, starting over here, we do have the AMD or Xilinx FPGA. This is an absolutely enormous SoC, a Zinc UltraScale Plus FPGA. It does, of course, have quad ARM Cortex processors in it, which is probably where the application is running. It does have over 650,000 logic cells, which can work up to 1.3 gigahertz. It does also interface with its own memory, where probably the firmware is running. 512 IOs. Yeah, it's pretty big, and it's not cheap. In individual, over $8,000 each. Now, this is going to interface with these custom ICs on the right side, gather all the data, process them, and of course, do all the firmware interactions to the outside. Now, looking at the rest of this board, it becomes really obvious why it is so difficult to compete with manufacturers who make their own ASICs when develop instrumentation, like Rohde Schwarz, Keysight, and Tektronix. A lot of the front end and a lot of the capabilities of this oscilloscope are because of the custom features inside of the ASICs. So we do have two identical ASICs over here. This is going to be all the memory acquisition, processing, and all the hardware accelerated features we talked about are going to be done in these ICs. And some of that may be offloaded into the FPGA, but given given that all the memory is over here, these are the acquisition memories of each 4 channels at a time, it's clear that a lot of processing is done locally over here. Another thing to note is that there are cages around all of these devices, and that's because there's a lot of digital activity, and you're going to radiate out broadband noise from all the interactions of these devices with each other. You want to keep that as contained as possible because you're just a few centimeters away from the acquisition front end. So not only all of this is custom, all the ADCs in the front end are also all fully custom, and the front end devices, the analog conversion devices in the front, are also fully custom. So yeah, if you remove those from this, there's really not much left. All the signal integrity and all the noise and all the bandwidth and the linearity you're going to get from the front end has to be brought in by the custom ASICs, and that's so hard to compete with. And if you look closely, there is another item over here that's also inside of a cage. This is actually a dual PLL with 8 independent output clock generator. And that's not the one responsible for the data converters, but nonetheless it is a 100 femtosecond grade part, allowing you to provide synchronous clock to these 2 DSP front ends. Now this is a digital system at the end of the day, so the sensitivity to jitter in terms of achieving signal to quantization noise ratio is not the same as the clock that's provided to data converters, but nonetheless everything needs to remain synchronous, and I'm sure there is a way to synchronize the main PLL for the data converters and this entire system. And of course this FPGA is also going to require a clock of its own, and that's why the multiple clock output of this is most likely helpful, creating a clocking system for the entire digital backend over here. And looking at the back of the board, you can see that the cage is extended to behind the BGA footprint as well. And that's because the vias connecting all the BGA pads go through the entire board, and they act like tiny little antennas, and they can radiate out all the digital noise into the board as well. So it's pretty important to cover all of that. There's also a clear break over here in the ground plane, and I'm sure the VDD planes between these two, because this is kind of the boundary between the mixed signal analog and the digital in the front end, because the data converters are over here. A lot of DC-DC converters, every time you see a cluster of inductors and capacitors, you do have a voltage regulated DC-DC converter section. If you also look carefully, you can see all the connectors that the user interacts with have individual screws holding them solidly to the board. First, this makes them easy to replace and also makes them really mechanically stable because the user is plugging and unplugging things into all of these BNC connectors. And that's the challenge where the user directly interacts with such a big board. You don't want to break anything because you really don't want to have to replace a board like this. But it looks like that they have thought about this. Lots of mechanical stability on these. Even the front-end connectors, these are 8 analog inputs. If I go back to the first page, there are screws holding those ones to the board as well. So a lot of thought has gone into the mechanical design. And of course, a critical part of every oscilloscope is the analog to digital converter. And here we see 4 ASICs. These are custom ADCs designed by Rohde Schwarz, and each of them is a 2-channel 12-bit ADC with 10-bit effective number of bits. And if you look carefully, you can see on the left side of every channel, we are feeding the first 4 channels of the oscilloscope. And if I go to the second page, the other 4 channels are feeding the other side of the package, taking advantage of the 2-channel ADCs inside of each package. Now, even though we are doing that, each channel gets its own dedicated 12-bit ADC with no sample rate limitation, so you can mix and match channels as you want, and that's pretty important. There's of course a high definition mode as well, where you can play with the sample rate and take advantage of the oversampling and get more effective number of bits from these ADCs. So the entire architecture of the DSP here in the back is actually 18 bits, and that's pretty critical because it means all the additional functions are running on that 18-bit architecture, so nothing slows down when you go into high definition mode. That's not an easy thing to do on its own. Each of these chips has to support 400 gigabit per second in order to accommodate the 4.5 million acquisitions per second and the 18 million waveform update rates. It's just a crazy fast oscilloscope. Now on top of that, because you do have this 18-bit architecture with the Fourier transform that you have built in, you still get the really fast FFT, 45,000 up to 45,000 FFTs per second, even if you're in the high definition mode. We'll see some of that as we're playing around with the unit. So it's not an easy front end, especially because you have to also get the memory and everything has to be interacting with each other. Now keep in mind that we do have this digital triggering architecture and some fancy digital functions in there, which I will show you. It also means that as you reduce the sample rate, you're still capturing those edges at the full rate because you do need that triggering, and that has some interesting consequences in the digital decoding of the architecture of the oscilloscope. So a lot of thought has clearly gone into it. There's another component over here which I could not really find the part number for, but I believe this is the PLL. There's a crystal, 100 megahertz crystal that feeds it, and this is likely providing the clocking required for these 4 ASICs and synchronizing them with the other PLL on the board. Now this PLL for the ADCs is pretty critical. We are dealing with 10 effective number of bits at a high sample rate, so you have to have very good jitter in order to even be able to accomplish that, and that's all coordinated, of course, among these different components. Now you can make all these beautiful data converters. It wouldn't matter if you don't have a front end that can maintain the noise and the linearity to be able to feed these signals all the way to these ADCs. And this front end itself is pretty complicated, made of a bunch of custom ICs with all the different functions and modes that it supports. So let's take a close look at it. Now the front end of this oscilloscope, much like every oscilloscope, has to convert a single-ended user input into some kind of a differential signal at the nominal input level of the ADC, almost always a fixed value. And that's not an easy thing to do on its own, and not every front end is the same. For example, in this particular oscilloscope, we do support some pretty impressive specs. First of all, we can support 400 volt peak at the input. That itself is tricky. You need to have careful protection circuitry for that. And then you can go all the way down to 500 microvolt per division, so you have to have pretty low noise, and you can do that at the highest bandwidth of the oscilloscope. At the same time, very low noise, 130 microvolt at the 1 millivolt per division, again at full bandwidth of 2 gigahertz, not easy, and you get to apply a 5 volt plus or minus offset to the input even at the 500 microvolt per division. Now you can imagine that that can be pretty helpful because you sometimes have noise on top of a signal with a fairly large DC value, and you can absorb that directly in the front end of the oscilloscope, saving you a lot of probing and other complications. Now you can do all of this because you do have custom ASICs in the front end, so we can follow the signal path, pun intended, and see what it does. I don't intend to do a complete reverse engineering, but we can learn a thing or two from the architecture. First, we do have this coaxial to strip line converter, and the very first thing we see is a relay. That relay can have several uses and advantages. First of all, it can switch between 50 ohm and high impedance mode. It can also serve as protection in case the 50 ohm path is being overloaded, because the maximum signal there is quite a bit smaller than in high impedance mode, and it can protect your 50 ohm termination that way. It can also be used for switching and calibration paths and so on into the front end. And the two paths look quite different, and on the other side you can come back all the way out, and this is a 50 ohm path almost certainly. We do have an interesting component over here. This is a delta sigma RMS to DC converter. There could be a few reasons for that. It can be used for detecting the overload condition, so you can quickly find out if the signal is too much and then switch away from the 50 ohm. It can be used for calibration. It can even be used for various measurements of the front end. And once you come into the 50 ohm path, you can see that there are several different possible paths that you can take over here. One of them even goes from the outside and comes back. This is the back side of the same thing, and that could be various attenuation settings and even filters in the front end for aliasing and so on. Ultimately, all of that ends up in this big IC, and this is the 2 gigahertz bandwidth IC, which conditions everything. This itself seems to have two different outputs. This looks like an LC filter over here, and perhaps that is part of, again, anti-aliasing filter in the front end. Now on the other side, we do have the 1 mega ohm input that itself needs its own attenuation, but it also has an AC and a DC coupling mode, and you can see series capacitors and so on in the front end. And there's another dedicated IC over here which will process that, convert that to differential, and it arrives here as well. So there's a chip in this one. That is most likely a switch, and that will switch and select between which of these paths ultimately gets over here, and that's the signal that's going to reach our ADC. And I'll explain to you minor differences between some of these channels at the same time. There is a very high precision 20-bit DAC over here, and that could be used for doing the DC calibration loopback of this, and perhaps some of that may be responsible for applying the DC offset, although I think that is almost certainly done inside of these chips in order to be able to be close to the analog front end. But yeah, this is probably a calibration thing, and there's one in every channel as a result. So yeah, pretty complicated. On the other side of it, you can see some further capacitors and attenuation resistors passive in the front, and another big protection circuitry here as well. Now if you look carefully, because some of the channels are routed to the ADCs on the front side of the PCB and some on the back side of the PCB, like for example these ones are on the back and then these ones are in the front, they don't arrive from the same side, so you have to compensate for that. And this is a very subtle point here. Let me see if I can show you. So up to this point things look the same, but then this guy is on the top of the board, and it goes through two sets of vias to go down and then back up unnecessarily, but it has to do that in order to match the number of vias between all the channels, so everything is completely matched. So there's a little tiny wiggle of the PCB traces over here completely unnecessarily, because they could just go straight obviously, But they're not doing that because they want to make sure the same number of vias shows up on all the channels, because this one does have to go through the board because it comes out on the other side. So there's a little subtle differences in the layout between them just to compensate things. A bunch of op amps and regulators and switches and analog muxes and all kind of stuff are scattered around over here to control everything, but you can see what it takes to make a complex front end to feed high performance ADCs. The front end of oscilloscopes is a work of mixed signal design on its own. A few other noteworthy things: we do have a 2-channel 1.25 gigasample per second 16-bit DACs over here, which are feeding two identical paths. You can see the differential lines on the PCB. These are the two outputs of the arbitrary function generator. They have their own relays for range switching. There is current feedback op amps and everything for condition the signal in the amplitude that you want, drive a 50 ohm output. They do have their own dedicated cages too, because they put a lot of signal. You don't want that again to interfere with everything else. Trigger input, reference input and output, and I think this DAC is directly driven from the Xilinx FPGA. Maybe this is its own dedicated memory, but either way, it's close to this for a reason. Everything else you see are either USB, Ethernet, controllers, and so on. Nothing unusual, a lot of digital parts. Here's the gig of memory, as I said earlier, per channel, which is optional. Lots of power coming in, of course, which is quite a challenge. This thing probably burns a lot of power, but surprisingly, it runs really, really quietly, as you will see. So they've done a lot of good work on the thermal side of this as well. It's amazing what it takes to make a modern, state-of-the-art oscilloscope these days. And here is our first setup. We have some board over here with various digital and analog activities on it, and there are some defects in these waveforms. We're capturing them directly on two of the channels of the MXO-5, and we want to see if we can use the advanced triggering functions to capture those flaws. Let's take a look. So let's see if we can analyze these signals. What you're looking at is the modern GUI interface for pretty much all of the Rohde Schwarz oscilloscopes, from entry-level models all the way to the RTP series. It's a pretty nice GUI. It's fast, it's internally consistent, things are easy to access, and I'm actually logged into it through the web by just simply typing the IP address into a browser, and they have one of the best remote interfaces like this. It's pretty responsive, as you can see. Everything pretty much can be accessed through this menu, and I'll talk about how the zone triggering fits into all of this, because it's a bit of a deviation from their original GUI design language. We'll talk about that. So for example, if I go to the vertical settings, I can see all the vertical settings on channel 1. Right now, channel 1 and channel 2 have exactly the same settings, and you can see the signal flow diagram over here. This is something that Rohde Schwarz originally started and is present in all of their instruments, including their oscilloscope. So everything is really quite nicely present. So for example, if I go into the acquisition, if I go under the speed here, I can see how many waveforms I'm capturing with this particular trigger. This is a very simple trigger I have set up over here. If I go over trigger here, it's just a single event trigger on an edge, rising edge of this waveform on channel 1. So going back onto the acquisition and looking at the speed, 176,000 waveforms per second is being captured, which means that 88% of the entire time is actually caught. This is a very, very helpful little sub-menu. So we can go ahead and make changes. For example, we can turn on high definition. Right? If I turn on the high definition over here, now I am capturing 16-bit, essentially displaying a much higher resolution through oversampling. But if I go over the speed over here, you can see that it makes no difference. That's because all the hardware acceleration is at an 18-bit architecture. So going to the high definition mode doesn't change the capture rate, which is super, super helpful. Let's go down and turn this off for a second, because it does limit us to 100 megahertz, although this signal is pretty low bandwidth. So let's say I want to find anomalies in this signal. Now you can see clearly, because we have such a high frame rate here, that you can kind of see that there are indeed some problems with this. Now normally setting up a trigger, once you know the problem, is not that difficult. It's often difficult to come up with the appropriate trigger for the flaw you're looking for. Of course, it's a chicken and egg problem in this case. But this zone triggering is a beautiful tool to guide you in the right direction, to make sure how the signal should be triggered and find those really tricky things to locate. Now, even though I see this ghosting over here, these events, these anomalous events, are actually quite rare. So if I press a single trigger, I can press that as many times as I want, and the odds of me catching that are almost zero. That's because we are catching so many waveforms. So we see the ghost image, it gives you the illusion that they're more frequent than they actually are. And that update rate itself is very helpful, because it gives you hints about the waveform problems. And if I do also single capture, occasionally I will catch a different edge, because I'm simply triggering on the rising edge. And that's the other reason why you see multiple ghost images of this, because again, there are so many trigger events. Now, this instrument natively supports a lot of the classic triggering events like glitches and widths and runs and windows and so on, and these are very, very helpful if you know kind of what you're looking for, and they're also quite fast. But let's see if we can stabilize this waveform and see if we can use the zone triggering to guide us onto the kind of problem and how fast that would be. So you can start doing this by pressing the zone button. As soon as I press the zone button, I will get a new menu at the top over here. And this is where I can add my various zones and areas to the waveform in order to selectively trigger on those sections. Now this thing deviates from the rest of the GUI language. This is the only thing that shows up here blocking everything. I can see why they have put it up here, because if they put it in these menus, it's going to overlap the waveforms, and you want to be able to draw on the waveforms without anything being in the way. But the problem is that it now hides everything else. Also, zone does not appear to be accessible in any of these menus, even though it has a dedicated button. I think some refinement of how this is done will certainly help. I'll make some additional comments as we go forward. So what's the first thing I want to do? Well, I want to stabilize this waveform, because as we saw, this waveform is jumping around depending on which edge is being captured. So why don't I force the instrument to abandon anything that is outside of that first trigger? Let's see how we can do this. I can add a zone on channel 1, and I can tell the instrument, you must make sure that the waveform does not intersect that region, and I can just draw it over here. And this is actually updated live, which is super cool. And look at that. Now I'm forced, the waveform that is being shown is only on these rising edges. All the other ones are being abandoned. I can also draw one over here, really trapping the waveform between these two exclusion regions. And now I can scale everything too if I want, and everything scales with it, and everything is completely stable. It is just so much fun to play with this. Now, if you look in the middle, it's clear that the anomaly is here. Remember, it doesn't matter if I do single triggers. I still will never catch that because it's so infrequent. So why don't I ask this now to ensure that the waveform must intersect this middle section? So I can now change this and put must and draw something in the middle. Now look at that. Just like that, I have isolated this problem. I can now zoom in and out. It doesn't matter. It's going to always show this. This is so much fun. We can also see that this waveform and this waveform are indeed not the same, and these anomalies are not necessarily happening at the same time. So we can analyze this a little bit further. I think I just saw one pass through. So that's pretty cool. Now, there is a penalty to pay for this. It doesn't come for free because this is a fairly sequential event. Let's see how it is actually doing that. So if I go under the trigger menu, what has happened is that the instrument is now doing a sequence of triggering. Basically, it triggers in condition A, and once it does that, it goes through the condition, which is the zone trigger. Now, condition A is what was before. It's just a rising edge. So it's just simply catching a rising edge, and once it does that, then it goes back and then tries to apply the zone triggering on top of that. And if I click on that, we can see all the zone information I have entered are here. Zone 1, 2, and 3. It must not intersect zone 1, it must not intersect zone 2, and it must intersect zone 3. And I can change this logical operation between these as well. And that's how it's isolating this particular section. Now, there's no back button over here. I think that's missing. There definitely should be one, because in order for me to go back to the previous menu of the trigger, I have to now go somewhere else to click on that. And I can also change this one to a different one. We'll talk about that in a second too. But you can see how easy it is to capture this. Now, this is a very classic runt situation. So we can do, now that we know what it looks like, we can actually define a runt trigger and compare the speed of the triggering, because as I said, there is a penalty to zone triggering. So let's see how many waveforms we're actually capturing in this situation. So if I go under the acquisition and I look at the speed, I'm capturing about, let's say, around 50 waveforms per second, which is under this zone triggering condition. Now I can disable the zone triggering and apply the runt trigger once I know what it looks like, and we can compare the speed. There's a few other things we can also do. You're not limited to only square. Of course, you can grab one of these points and move it around, or you can even add a point to it. And if you add a point to anywhere here, you can create essentially any arbitrary waveform. And it's pretty touch friendly too, so they've clearly thought about this. So let's go over here and let's get rid of all of these, erase them completely, easy to erase. I can erase this one as well. Can erase this one too. Now the waveform is again jumping around everywhere because we don't have any of those triggering. Let's go into the trigger menu and let's change that to a single event. But now let's choose from here the runt condition. Okay, and I can put the upper one up here. The mouse wheel works, which is good. Thank you for that. And the bottom one here. So I can also catch that this way once I know what it looks like. Again, this is a very simple case on purpose so we can compare them. Now if I go on to the acquisition and I look at the speed, I'm catching 300 waveforms per second. So on average, about 5 or 6 times slower once you do the zone triggering. But that shouldn't surprise us because the zone triggering is a sequential event. First, the first one has to be met, the condition, and then the filtering is done. The fact that it runs as fast as it does is already really remarkable. You can almost trigger on a pixel on the screen, which I don't think any other scope can really do that, at least not as sophisticated as this one. So now we can understand that the penalty to pay there. But it becomes even more powerful when we add areas as well as zones, because now we can do it across multiple channels and correlate them to each other and even apply logical operations between the areas. So I've gone ahead and reproduced this zone triggering on channel 1. Now I want to find out if this kind of glitch is happening on the second channel at the same time as it is happening on channel 1. That's pretty difficult to catch. Now we can do this by now adding, instead of areas to the zone, but an entire new zone. So if I go to add zone, I can select which channel I want this zone to be added. This time I want to add it to channel 2. Now I get to draw again. So I'm going to draw another one over here, and I'm going to wait to see if they ever happen at the same time. And look at that, they do. In fact, they do happen at the same time, but it's extremely rare. I think the event at the bottom is 1,000 times less frequent than the event at the top, but every once in a while they do happen to have at the same time. This is normally very tough to catch. And not only that, if I go into this settings over here and see what's actually happening, you can see that I have defined the first zone, that's the one on channel 1, with these logical operations, and I have defined only a single area in zone 2, doesn't have a lot of logical operations anymore, but now I can apply a super logic on top of the zones. And if I go over here, you can see that we're triggering when zone 1 conditions and zone 2 conditions are simultaneously met. And if I click on that, I can change the trigger condition on top of this. So you can come up with some complex and unusual set of triggers. I can find out if these events happen at the same time, or if there is a situation where they don't happen at the same time. I can do exclusive ORs. I can do all kind of really unusual things across many zones at the same time. It can be actually overwhelming in terms of the number of complex things you can add. Now, one feature I wish it had, again, there should be a back button, it's missing over here, but if I turn off the display, it actually doesn't stop the triggering on it. So there should be an enable and disable button on top of a display button, because sometimes I make all these careful drawings. I don't want to erase them just to disable them. But right now the only way for me to disable this, as far as I can tell, is just to erase the zone. And then of course it goes away. But I don't want it to be done that way. I should have an enable and disable so I don't lose my drawings. But hopefully you can see how sophisticated this can be. And once you again find the flaw, then you can do other things to speed the triggering up if it's needed. But to just do all these weird logical operation and trigger on some pixel here and some pixel there and do exclusions between them, very nice. I really like this idea. Let's quickly take a look at another example. So here we have a series of pulses. This is a pretty slow waveform. You can see the time scale is on 50 millisecond. And if I go into the acquisition, look at the speed, we're really only catching about maybe 10 waveforms a second. We're catching a pretty good amount of time of that waveform. So let's say I want to isolate a defect in this. Now I can do a single trigger. This is a pretty slow waveform, and you can see that the pulses are always on the positive and negative, but there's a gap over here. And every once in a while, there's a gap where you have the positive pulse, but not the negative pulse. And I want to trigger on that. Well, we now know that it should be pretty easy to do this. If I go under zone, I can add a zone where we must intersect, and I can keep that intersection here in the middle. So right now nothing really changes because of course there's going to be always a rising one. But if I want to make sure there is no falling edge over here, I just simply change that and say, well, make sure there is no falling one over here. And I let that run. Under this, now we have captured and the waveform is stable. Now another thing you can do in this situation is that you can offset the trigger, basically keep these two areas over here, and then say, well, make sure that actually what I really want is I want to make sure that there is nothing here and there's nothing here. Now this doesn't seem to do anything differently, but now I can go back and erase these ones. And that can be an interesting thing in itself, because if I erase them, I simply get a stable waveform again. So you can also have a situation where the triggering is done at the side and the edge of the waveform, as opposed to the main waveform itself. Now this is of course going to be slower again, because this is not a very frequent event to begin with. Now, if I go into the acquisition and take a look at that, yeah, we're catching maybe a couple of waveforms a second. That's normal. We know that it's going to slow down in that case. Now, if I go over here and go into the acquisition and change the speed, go into the HD and change the state to high definition, nothing really changes. We're still capturing the same amount of waveform. We have now the better resolution. We can see all the minor details of the rising and falling edges. Yeah, so you can do these interesting movements and push the trigger to be somewhere that it traditionally is not, and align it potentially with other events in the waveform. And here's the setup of our next experiment, which is considerably more complex. At the heart of it, we have an IQ up converter. The output of the IQ up converter is directly connected to channel 1 of the MXO-5 series, so we can analyze the RF signal. The I inputs, the I and Q signals, are coming from the dual arbitrary function generator, which are coming out of the side of this instrument. So that's also generated by the MXO-5. The yellow signal coming here from the right side is coming from two sources combined. One is sitting on the bench, which is a portable signal generator, and the other one is the Rohde Schwarz SMBV100B. The teardown of all of these things I have done also on my channel, so you can take a look. Now, the purpose of this is to create a really complex IF behavior and a lot of unusual things happening in the RF domain, so we can see if the MXO-5 can analyze that. Now, at the same time, this instrument is ridiculously quiet. It actually makes almost no noise at all. All of Rohde Schwarz instruments are very good at thermal management and making sure it doesn't generate any noises. They're probably one of the best in the industry at that. So let's take a look and see what we can find. So here's our waveform on channel 1. There is a lot going on here. It's very difficult to discern anything in the time domain. First thing first, let me make this into a 50 ohm signal. It is coming from a 50 ohm source from the mixer, and it looks good. Let's go and turn on channel 2 and channel 3. Those are our IQ signals, and then we can just drag them around to put them in a way where the screen is a little bit more organized and we don't block anything out. And look at that. There you go. So we have all of these three channels. Now I want to look at the spectrum of channel 1, and that's one of the other areas where this oscilloscope really shines. Let me show you how fast it is. You can actually reach it from up here. By the way, I might have changed my mind a little bit about the placement of these, because if I click on individual ones, they do indeed change the menu at the top. So there is some contextual consistency with the use cases here. Some of the other comments about adding a back menu and being accessible from this main menu is still true, but it's growing on me a little bit what they're doing with this top menu here. And under the spectrum menu here, we can see that we can have up to 4 of these hardware accelerated spectrum views, these FFTs, and you can apply them to any channel. They can have any center frequency, any span, any resolution bandwidth, and they're not tied to the time domain settings at all. They're completely independent of each other, which is of course very helpful. So let's go and enable this one. And here it is, and check it out. Look how fast this is. It's almost like a real-time spectrum analyzer, except that this is of course an oscilloscope, and you can look at this anywhere, even at the entire full 2 GHz span. Now here we're looking at 400 megahertz with a span of 75 megahertz, because this is the RF output of our mixer. We want to see what's going on around it. And looking at this spectrum, there is a ton of activity, a lot of tones. We have no idea how these are behaving. And this is why the time domain signal is so useless at this point, because it's just too complex in the frequency domain. Now I can go over here and look at the peak list, for example, enable that, and we can see the frequencies of these peaks. And some of them come and go. That tells you a little bit about potentially what's happening to those tones. Let's go and turn this off. Let's go and add another one. We're going to look at exactly the same channel again, channel 1, but this time we're looking at 800 megahertz with a different span. This is now twice the RF frequency. Normally a good mixer should not put out anything at the twice LO frequency, but in this case, let's take a look and see what it does, and indeed there's something coming out. So let me rearrange this a little bit so we can analyze it a bit better. So here we go. You can see at twice the frequency we do have some tones. It's not quite as symmetric as it is at the lower frequency, and that has to do with the way this mixer is operating. But let's go and see if we can figure out where this FFT is actually calculated. Now I've selected channel 1, and I can zoom out into a much larger time scale, and you can see that nothing changes with regards to the spectrum. If you look closely, there's 2 different regions here. One region is a little bit wider than the other one, and this is the gate of these FFTs. That's where these Fourier transforms are calculated. And the duration of that has to do with how you set up the resolution bandwidth, the span of these settings. So if I click on this, this window knows that there are multiple things being displayed on this top left. So it's asking me which one of these do you want to select. Well, I want to select the gate. And if I move it around, you can see the bottom Fourier transform calculation changes. And as I move it around, interesting things are happening. And it tells us that this waveform is rapidly changing across time. And by moving this around, I can select and find out where I want to analyze with respect to the trigger point. Now remember, this is just still basically just an edge trigger that I'm doing, nothing unusual regarding that. And we're taking, let's see how many acquisitions we're actually making about 2.4 thousand acquisitions per second, which has to do with how fast this thing can trigger on this waveform. So you can also adjust this gating by going into the spectrum menu, selecting the FFT you want, and adjust the gate. So if I put this back to 0, it's going to put that gate down the middle again. So it's pretty all straightforward, very intuitive on how you can manipulate this, and I like the way the waveforms are getting selected. So we're back on a 1 microsecond record length again, and let's do a couple of single triggers and see if we can discover anything about this waveform. So I do a single trigger, and you can see we see a tone here, and we see a tone here, and we indeed see the carrier, and there's 2 on each side. Let's do another single one, and look at that. Those 2 tones are now in a different place. So they're not there at the same time, or are they? And if they are there, it would tell us something about how they transition from one of these tones to the other tone. If I keep doing single triggers, you can see sometimes they're on the outside, sometimes they're on the inside, but there must be a way when they transition from one to the other. This is really hard to catch. It's very hard to catch because there are multiple frequencies here present. It's a very complex spectrum. I'm not sure actually how I would do this in any other instrument. You'd have to be quite creative, but here it makes it super easy. So let's go ahead and put this into normal trigger. It is already. I'm going to select this, and we're going to now enable zone triggering, except that I want to apply this zone triggering now to our spectrum. I can apply it to anything, of course, and to the spectrum is going to now isolate this. So what do I really want? I want to capture a situation where this tone and this tone really is present at the same time. So I'm going to put the intersection as a must. I'm going to draw one here. So right now I'm catching all the ones where it is here. I'm going to add another one. I'm going to force to catch all the ones that are here too. And look at that. Now every time I do a single trigger, I'm catching both of them. This is a pretty interesting piece of information because it's now telling us what happens between these 2 points. And I can go ahead and zoom out the waveform so I can see the actual gating. There you go. There's our gating over there. Now if I do a single, check out what I can catch. Now I can actually see that transition point on the IF input while triggering it on the RF output. That's pretty interesting and unusual, certainly for oscilloscopes. Let's go over here. Now we can apply the zoom function, and we can select, close that, apply the zoom, and we can select where the zoom is being applied. So I want it on waveform number 2, so I'm going to select diagram 2, and then we're going to get rid of that, and we can move this around, and look at that. There it is. We catch it, and it is telling us that the IF is jumping between 2 frequencies. That's the first frequency, and that's the second frequency. And if I zoom out in time a little bit more, and I move this around, I can even catch exactly how this transition happens. And by the look of it, it is transitioning very sharply, and that's because the IF has a frequency shift keying on it that is a square wave itself, so it's just bits toggling back and forth. That would be really hard to catch in any other situation. So hopefully you can appreciate how subtle this measurement actually is and how easy it becomes to isolate this. But we don't have to stop there. We can do some additional analysis on this waveform. What else can we discover about these waveforms? Well, what about these outer tones? These outer tones don't seem to be moving around. If I do a bunch of single triggers, you can see they're always in the same place, but they don't always seem to have the same amplitude. So perhaps something is going on with the power of the signal at the IF port causing the value of these signals at the RF changing. Well, can we isolate that? Well, indeed we can do this. We just have to enable the zone. Now this time I want to find out when these things reach their lowest value, so we can see a transition point when they are completely gone to when they're at their fullest value. So how can I do that? Well, now I'm going to choose a situation where the square I'm going to draw should not intersect the waveform. And I'm going to draw a little one over here and leave it like this. Look at that. Every time I do a single trigger, that waveform can never be in that zone, so the amplitude is smaller. But now I can also select it and push it further down by selecting this edge and bringing it down, and see how low I can bring it. Now, every time I trigger that, I see amplitudes that are even smaller. And check it out, the signal here has all completely disappeared within this time window we are looking at it. That's because we are forcing the trigger to be when these signals are almost completely gone. This again would be very, very difficult to trigger on in any other situation. Now I can also go ahead and zoom out, and I would expect that waveform to be at its lowest value if I zoom out far enough. And check it out. Look at that. That's exactly what we were expecting to see. This is where the IF disappears, and that is where we are limiting ourselves to where to trigger. If I grab this and grab this tail side and bring it even lower, I'm going to limit myself to even smaller signals, and you can see that we are at the minimum point of this. This now is telling us that the signal coming in at IF is an AM modulated signal, and that's why the amplitude is changing on both sideband at the same time. Very nice way to trigger on this signal again. Of course, once you do this, you can discover what's going on. You may not always have access to every signal. I'm just doing this for a demonstration, but there's a lot more going on here. We can even dig in deeper. So let's take a look at now some of these other spurious activities that are happening around. Sometimes it's important to find out if some activity is actually uncorrelated to the other desirable activities in the system. So let's see if that's the case, or are these harmonics of all these other tones that we're purposely generating ourselves. So let's now look at this one. It doesn't really matter. They clearly are related to each other. So let's do a zone triggering one more time, but this time we're going to do it on spectrum number 2, the one over here at a higher frequency, and I want to isolate, let's say, this one. I'm going to draw a square around this one, and we're going to wait a little bit, and keep your eye on this side of the screen. Look what happens. Every once in a while something comes up and it disappears. Now why would that be? If you think about this, what we're doing is that we're always triggering at a point where this tone is present. Now, this tone every once in a while is going to coincide from the time that we're jumping from this frequency to this frequency. And every once in a while, they beat with each other and essentially alias with each other. And you see those two tones. So we have a rolling window of this gating FFT that sometimes lands on that transition. Now, this gives us a critical piece of information, and that is that this signal is not correlated to the frequency of our frequency shift keying signal. That's a huge piece of information. Again, I'm not sure how else you would discover this, that these are not actually related to each other. It's pretty nice to be able to do all of this, but clearly they're interacting with each other in some way. That's another very nice way of finding unusual behavior in an RF domain. And all of these zone triggering that we can apply can be applied to the waveform live, but they can also be applied directly to the history of the waveforms that have been recorded. So you could have had something, you can play it back, you can do your zone triggering on it, and then if you're not happy about it, you just do a new zone triggering on the same waveform. And that can be also pretty helpful, because sometimes an event is really rare, and if you have a window that has that event in there, you can do further analysis over and over on again until you find out what it is that you're looking for. So it's pretty good to do this. And of course, we saw the logical operation between different zones and areas. Here I'm actually doing somewhat simple triggering using this mechanism, because when you have multiple zones and multiple areas across both time and frequency domain, you can start creating some very crazy kind of triggers that relate different windows to each other, different waveforms together, even trigger something that correlates in the time and frequency domain at the same time. This is it becomes almost overwhelming in the creativity you can have to trigger on various things. And in case you wanted to see where I'm generating these IF signals and what they look like, that's just under the generator. So one of them is going to be a sine wave, and if I look at the modulation, it's an AM modulated signal at the 1 kilohertz and 100% extinction ratio. That was the waveform that we saw the amplitude changing. And on the generator 2, I'm generating a sine wave, which is an 8 megahertz carrier frequency, and it has a frequency modulation on it, jumping between two frequencies, also at the rate of 1 kilohertz. So that's how I created this complex setup. These other spurious tones are coming from that handheld additional generator that's imposing itself on top of the existing LO signal. That's why the spectrum becomes super complex. In the situations where you may be doing some EMC pre-compliance, seeing a very complex spectrum all over the place with signals coming in and going is very common, and you may have one tone that is violating your mask, and you really want to nail down and find out where it is coming from and what it's correlated to, and this tool would be absolutely invaluable in situations like that. And there you have it. I hope you enjoyed this video. There's of course so much more you can do with these oscilloscopes. It would take hours to demo everything, but I wanted to show you some of the differentiating features so you can appreciate how this new triggering system and time and frequency domain comparison can help you debug your systems. Let me know what you think in the comment section. I'll see you next time.